Optimise technology, the bicycle re-invented. Tim Rouhani. The multi-layered blueprint designs. Most people view optimization as a digital process, tuning an algorithm or upgrading a server. But true optimization begins with the human element. It is the process of taking raw, unrefined circumstances and iteratively improving them until they yield something extraordinary. My journey didn't begin in a Silicon Valley garage or a high-tech lab. It began in the soil. The farmer's patience. As a young Albanian boy, I was raised as a farmer. Farming is the original technology. It is the study of inputs and outputs. You learn quickly that you cannot rush the harvest, but you can optimize the environment. You learn the value of hard labor, the unpredictability of the elements, and the necessity of being resourceful with what you have. Those early mornings in the fields instilled in me a ground-up perspective that I carry into every technical challenge today. Starting from scratch, the immigrant's trial. At age 15, my world shifted. I arrived in New Zealand as an immigrant with my family, facing a landscape that was as foreign as the language. At an age when most teenagers are finding their social footing, I was starting from zero. I was a beginner in English, sitting in classrooms where words felt like static. This was my first experience with a system crash. To survive, I had to rebuild my communication operating system from scratch. It taught me humility, but more importantly, it taught me how to learn. When you start with nothing, every piece of knowledge is a hard-won asset. The renaissance of the hands. Before I ever learned any theories, I mastered the physical world. My career path was a series of diverse vocation modules. The mechanic, I learned how complex systems work under the hood while studying at Selwyn College, Auckland, New Zealand in early 2000s. If one part fails, the whole machine stops. This is where I learned about the importance that every bolt counts. The house painter, I learned that 90% of a quality finish is in the preparation. Optimization is often invisible, it's the sanding and the priming that makes the final coat shine. The illustrator and musician, these were my creative outlets. They taught me that technology without soul is just cold metal. Whether through a pen or an instrument, I learned the importance of user experience, how a creation makes someone feel. The Soul Trader, 2013-2024. In 2013, I transitioned into the world of entrepreneurship as a sole trader. For over a decade, I became well versed in many aspects of business, building tools and mechanics in general. Running a business alone is the ultimate optimization test. You have a finite amount of time and energy, the hardware, and a mounting list of tasks. Between 2013 and 2024, I didn't just build a character for business, I built a methodology for efficiency. I learned how to automate the mundane so I could focus on the meaningful. I am not a technologist who grew up in a bubble. I am a farmer, a builder, a mechanic, and an artist who saw how technology could be the ultimate lever for the human spirit. Invention 1, the Guardian Grip, innovating safety on two wheels. The wind whips past, a blur of scenery accompanies the rhythmic pedaling, and the world rushes by in an exhilarating symphony of speed and freedom. This is the essence of cycling, a pastime, a sport, and a mode of transport enjoyed by millions. Yet, beneath the thrill lies an inherent risk, an unpredictable element that can transform a joyous ride into a moment of peril, the accident. While helmets protect our most vital organ and knee pads shield our joints, one crucial area often remains vulnerable, our hands. The very instruments that grip the handlebars, control the brakes, and steer our journey are frequently the first point of contact with the unforgiving ground in a fall. It was this realization that sparked the genesis of the Guardian Grip, a revolutionary handguard designed not just for comfort, but for unparalleled protection in the event of an accident. Imagine a handguard that seamlessly integrates into the bike's existing structure, a sleek extension of the handlebars that cradles your hands, absorbing impact and deflecting forces that would otherwise lead to scrapes, fractures, or worse. This isn't a bulky addition, it's an intelligent evolution of a basic component, transforming it from a simple grip to a vital safety feature. The core of the Guardian Grip's innovation lies in its sophisticated design, meticulously detailed in the accompanying blueprint. At first glance, it appears as an elegant, curved extension, but within its form lies a confluence of engineering principles aimed at maximizing safety. Let's delve into its key features. The integrated protective frame. Unlike traditional handguards that offer minimal lateral protection, the Guardian Grip features a robust, C-shaped frame that extends forward and downward from the handlebar. This frame acts as a primary barrier, creating a protective cage around the hand. In a direct impact or slide, this frame is designed to strike the ground first, dissipating kinetic energy across its surface rather than concentrating it on the delicate bones of the hand. Dual bend impact zones, Bend I and Bend II. The design incorporates two distinct bends in the protective frame, cleverly labeled Bend I and Bend II. These aren't merely aesthetic curves, they are engineered flexion points. Bend I, closer to the handlebar, is designed to absorb initial, lighter impacts. Its curvature allows for a degree of controlled deformation, much like a car's crumple zone, spreading the force and reducing the shock transferred to the rider's wrist. Bend II, further out, provides a secondary, stronger point of resistance, crucial for higher energy impacts or slides. This dual bend system ensures a graded response to various accident scenarios, offering progressive protection. Adjustable bend for personalized fit and optimized protection. Perhaps the most groundbreaking feature is the adjustable bend. This pivotal joint allows riders to customize the angle and extension of the lower portion of the hand guard. Why is this so crucial? Firstly, it caters to individual hand sizes and riding preferences, ensuring a comfortable and ergonomic grip without compromising safety. Secondly, and more importantly for protection, it allows riders to fine-tune the guard's position to best shield their hands based on their riding style and potential accident angles. A more aggressive rider might prefer a slightly more extended guard, while a casual commuter might opt for a more compact configuration. This adaptability ensures that the Guardian grip is always optimally positioned to intercept impact. Material science for superior strength and lightweight design. While not explicitly detailed in the initial sketch, the envisioned Guardian grip would utilize advanced materials such as aerospace-grade aluminium or carbon fiber composites. These materials offer an ideal balance of high strength-to-weight ratio, ensuring the guard is robust enough to withstand significant impact without adding unnecessary bulk that could affect bike handling. The internal structure would likely incorporate energy-absorbing polymers in key areas, further dampening impact forces. Beyond the fall, enhanced grip and control, it's important to note that the Guardian grip isn't solely reactive. Its ergonomic design, even without the protective benefits, enhances the rider's grip and control over the bike. The secure enclosure around the hand provides a more stable platform for steering and braking, especially during bumpy terrain or sudden maneuvers, potentially preventing accidents before they even occur. In a world where cycling safety is paramount, the Guardian grip represents a significant leap forward. It's more than just an accessory, it's a proactive measure, a silent guardian that stands ready to shield the most vulnerable part of a rider's control system. The subsequent chapters will delve deeper into the biomechanics of hand injuries in cycling accidents, the rigorous testing protocols for the Guardian grip, and the tangible impact this innovation promises for the safety and confidence of cyclists worldwide. The journey of two wheels just got a whole lot safer. Invention 2. Impact mitigation, the mechanics of the shock-absorbed rear grip. In the split second of a collision, the primary goal of any safety system shifts from prevention to energy management. While the front hand guard, discussed in Chapter 1, provides a physical shield against abrasion and direct strikes, the rear section of the Guardian grip focuses on a more complex challenge, reducing the deceleration forces transmitted to the rider's skeletal system. By integrating a dedicated rear handle equipped with calibrated shock absorbers, the design aims to transform a rigid impact into a controlled, soft stop event. The physics of the dead grip. In a typical bicycle crash, the rider's instinct is to maintain contact with the bike. However, a rigid handlebar acts as a direct conduit for kinetic energy. When the bike hits an obstacle, the energy travels instantly through the frame and into the rider's wrists, elbows, and shoulders. The optimized safety design introduces a decoupled rear handle. Instead of being bolted directly to the frame, this handle is suspended by a miniaturized hydraulic or spring-based damping system. Key components of the shock-absorbing handle. Linear damping pistons, situated within the horizontal bar of the guard. These pistons allow the rear handle to give by 20–30 mm upon impact. This small distance is critical for increasing the impulse time t, which significantly reduces the average impact force. Invention 3. The Symphony of the Brake, bicycle bell songs. Riding a bicycle is often celebrated for its silence, the quiet hum of tires on asphalt and the rhythmic clicking of a well-oiled chain. However, the innovation of bicycle bell songs transforms every deceleration into a deliberate performance, turning the mundane necessity of braking into a personalized musical experience. The musical wheel, design and mechanics. The joy of this system lies in its mechanical elegance. Unlike electronic speakers, the melody is physically woven into the wheel's rotation. The 7-note spoke system. The wheel is equipped with a series of calibrated strikers or tabs positioned along the spokes, capable of producing 7 distinct notes. Melody customization. Through the Choose a Melody interface, riders can adjust which strikers are active, essentially programming a physical song into the spinning wheel. Braking activation. The system is engaged via a dedicated pull bell lever. When the rider prepares to slow down or stop, pulling the lever activates the mechanism, allowing the rotating wheel to play through the selected notes. The fun of musical deceleration. The true magic of bicycle bell songs is how it shifts the rider's relationship with their surroundings. Braking is no longer just a safety response, it becomes a way to communicate and entertain. 1. Anticipation at the intersection. Standard bells are often startling or utilitarian. In contrast, a bicycle that sings as it approaches a stoplight creates a sense of whimsy. Pedestrians and fellow cyclists aren't just warned of your presence, they are treated to a fleeting, 7-note concert that dissipates as you come to a complete halt. 2. Mastering the tempo. Because the melody is tied to the wheel's rotation, the tempo of the song is directly controlled by the rider's speed. A fast approach results in a lively, upbeat trill, while a slow, controlled stop stretches the notes into a languid, melancholic refrain. This allows riders to perform their stop with artistic intent. 3. Personal expression. With the ability to choose different melodies, a rider's bicycle becomes an extension of their personality. One cyclist might prefer a bright, ascending scale to signal their arrival, while another might choose a familiar folk tune. The act of pulling lever 2 to activate becomes a signature move, a way to leave a musical footprint on the city streets. Safety through sound. While the primary focus is fun, the bicycle bell song system enhances safety through auditory visibility. Traditional brakes are silent, but a singing wheel provides a continuous acoustic cue to everyone nearby that a bicycle is slowing down. It replaces the harsh screech of brake pads with a harmonious warning, making the urban environment just a little bit kinder. In the end, this design proves that safety equipment doesn't have to be purely functional. By integrating music into the physics of braking, the bicycle becomes more than a machine, it becomes an instrument of joy. Invention 4. Traction redefined. The all-wheel drive (AWD) mountain system. While traditional mountain bikes rely solely on the rear wheel for propulsion, the conceptual dual-chain AWD bicycle represents a paradigm shift in off-road engineering. By harnessing power from the rider's pedaling and distributing it to both the front and rear wheels simultaneously, this system offers unparalleled traction on loose gravel, mud, and steep technical climbs. The mechanics of front-wheel propulsion. The core innovation of this AWD system is the mechanical linkage that transfers torque to the front fork without interfering with the rider's ability to steer. Integrated gearbox and bevel gears. A sophisticated series of bevel gears is mounted around the head tube. As the rider pedals, power is sent forward to a primary gear that remains stationary relative to the frame while rotating a secondary gear attached to the steering column. The front-wheel drive chain. From this steering integrated gearbox, power is transferred down the fork via a dedicated front-wheel drive chain. This chain engages with a specialized hub on the front wheel, providing active pull that complements the push of the rear wheel. Steering independence. The arrangement of the gears allows the fork to rotate left or rotate right freely. Because the drive gears are concentric with the steering axis, the chain tension remains constant regardless of the handlebar angle, ensuring a smooth drive forward motion even mid-turn. Optimized safety and control. An AWD mountain bike demands a braking system capable of handling the increased momentum and unique handling characteristics of dual traction riding. Dual rotors and high-performance braking. To manage the power of two-wheel drive, this design utilizes oversized rotors on both hubs. This provides the high torque stopping power necessary for descending aggressive terrain. Impact shock steering. Integrated into the steering assembly is the shock-absorbed steering system. Equipped with the Knight Rider handles, this mechanism uses dedicated shock absorbers to dampen head-on forces. This is especially critical for AWD bikes, where the front wheel may hit obstacles with more force due to active propulsion. The AWD advantage in the wild. The practical benefit of the AWD mountain bike is most apparent in low-bite scenarios. On a traditional bike, a rear tire spinning in the mud often results in a lost climb. With AWD, the front wheel's drive chain forward provides the necessary grip to pull the bike through the obstacle. Invention 5. The subtle revolution. The bicycle, a marvel of human ingenuity, had seen countless iterations since its inception. From the bone shaker to the sleek carbon fiber racers of today, each design pushed the boundaries of speed, comfort, and efficiency. Yet, for all its advancements, one small, persistent inconvenience remained a universal bane for cyclists: the flat tire. It was a scenario etched into the memory of every rider: the sudden hiss, the wobbly descent into immobility, and the inevitable fumbling for a separate, often forgotten, pump. Roadside repairs, while character building, were rarely enjoyable. This ubiquitous problem, seemingly minor, gnawed at the edges of the cycling experience, a tiny thorn in an otherwise beautiful rosé. For years, inventors had toyed with integrated solutions. Some bikes offered mini pumps clumsily clipped to the frame, easily lost or rattling loose. Others experimented with tire sealants, effective but messy and not a true solution for a complete flat. The ideal, a truly seamless and always present inflation system, remained elusive. Then came the pump lock, as its early prototypes were affectionately dubbed. Its genesis wasn't in a grand research lab, but in the cluttered workshop of Tim, also known to his Albanian peers as paytime designer with a sharp eye for utility and an intense dislike for unexpected detours caused by deflated rubber. Tim's inspiration stemmed from a simple observation: the handlebars, a constant point of interaction and control, were largely hollow. A wasted volume, he mused, a missed opportunity. His initial sketches were rudimentary, but the core concept was clear: integrate a compact, efficient air pump directly into the bicycle's steering column. The idea wasn't just to hide a pump, it was to make it an extension of the bike itself, a tool so naturally integrated it felt like it had always belonged. The greatest challenge lay in miniaturization and seamless operation. A functional pump needed a piston, a valve system, and a way to connect to the tire. Tim's breakthrough came with the realization that the hollow stem of the handlebars could act as the pump's main cylinder. A clever, spring-loaded piston mechanism was designed to fit snugly inside, with the top cap of the steering column doubling as the pump's handle. Pressing down on the handlebars would activate the pump, drawing air in and compressing it. The connection to the tire was equally ingenious. A thin, flexible hose, almost imperceptible, would run internally from the pump mechanism down through the fork, culminating in a small, easily accessible connector near the front wheel. A hollow pin, as Tim termed it, would allow the hose to connect directly to the tube's valve stem, creating an airtight seal with a simple twist. But Tim didn't stop there. Recognizing the growing popularity of air suspension in modern bicycles, especially for comfort and off-road capabilities, he saw a dual-purpose opportunity. What if this integrated air system could also serve as a shock dampener? By diverting a portion of the compressed air, or even by designing a separate, smaller channel, the steering column itself could offer a subtle, adjustable degree of suspension, absorbing minor road vibrations and enhancing rider comfort. Invention 6. The emergency foot brake, a return to instinct. For all the sophisticated engineering that went into modern bicycles, hydraulic disc brakes, electronic shifting, advanced suspension systems, there remained a certain primal elegance to the act of stopping. Before cables and calipers, before hand levers and friction pads, there was the simple, undeniable force of direct contact. Every cyclist, regardless of their age or experience, held a shared memory, a half-forgotten skill from childhood: the art of the emergency foot brake. It was born of necessity, usually when the primary braking system of a cherished, often battered, bicycle finally gave up the ghost. The squealing of worn-out rubber, the terrifying lurch as a caliper failed to grasp its rim, the sudden realization of uncontrolled momentum. In those moments, instinct took over. A shoe, often a scuffed sneaker, would be jammed against the rear tire, the sole grinding against the rubber, sending up a faint, acrid smell of burning tread and a surprisingly effective slowing force. It wasn't elegant, it wasn't quiet, and it certainly wasn't kind to footwear, but it worked. It was a raw, visceral connection between rider and machine, a testament to ingenuity born of desperation. Tim, aka Python, the visionary behind the pump lock, knew this instinct well. He'd worn out countless shoe soles himself in his youth, learning the hard way that sometimes, the most reliable brake was the one attached to your leg. As he matured and delved deeper into bicycle design, he couldn't shake the memory of that raw, effective stop. In an age of increasing complexity, he wondered, could there be a place for such a direct, intuitive braking method, but reimagined for safety and practicality? His focus, however, shifted from the rear wheel to the front. While stepping on the rear wheel was effective, it carried the risk of skidding, especially on loose surfaces, and offered less stopping power than a front brake. The front wheel, with its direct connection to the ground and its role in distributing the rider's weight, was inherently more efficient for deceleration. But how to engage a front wheel with a foot without sending the rider over the handlebars? The answer, Tim realized, lay not in the tire itself, but in the fender. Most urban and commuter bikes already sported front fenders, designed to deflect road spray. What if this seemingly passive component could be re-engineered into an active safety feature? His concept was simple yet revolutionary: a robust, specially designed front fender that could, in an emergency, be depressed by the rider's foot. This emergency foot brake fender would be mounted on a pivot mechanism, allowing it to rotate slightly downwards and inwards when force was applied from above. The inner surface of this fender would be lined with a durable, high-friction material, perhaps a reinforced rubber or a composite brake pad material, that, when engaged, would press directly onto the rotating front tire. The design challenges were significant. The fender needed to be rigid enough to withstand the force of a foot, yet flexible enough to pivot smoothly. The friction material had to be highly effective without causing excessive wear to the tire or locking it up completely, which could lead to a dangerous over-the-bars scenario. A spring-loaded return mechanism would ensure the fender instantly disengaged once the foot pressure was removed. Tim envisioned it as a secondary, auxiliary braking system, not a replacement for traditional hand brakes. It was for those moments of true emergency, a cable snap, a hydraulic failure, or even just a sudden, unexpected obstacle demanding an instantaneous, intuitive response. Imagine approaching an unforeseen hazard, and with a swift, instinctive downward motion of the foot, engaging a powerful, controlled deceleration. It tapped into that childhood memory of stopping, but refined it, made it safer, and directed its power to the more efficient front wheel. The emergency foot brake fender was more than just a new component, it was a philosophical statement. It embraced the wisdom of raw, human instinct, integrating it with thoughtful engineering. It offered an unparalleled sense of control, a fail-safe born from the simplest of actions, a nod to the past, and a clear path to a safer future on two wheels. Invention 7, the 5-gear drive, simplicity redefined. For decades, the bicycle's drivetrain had been a testament to increasing complexity. From rudimentary single speeds, we'd progressed to multi-cogged rear cassettes, intricate derailleur systems, and an ever-growing number of gears. While offering unparalleled range and efficiency, this complexity came at a cost: maintenance, potential for misalignment, and the dreaded chain suck that could jam the delicate machinery. For many casual riders, the sheer number of gears became overwhelming, a puzzle rather than a tool for enjoyment. Tim, ever the one to strip away unnecessary layers, looked at the modern drivetrain and saw an opportunity for elegant simplification. His vision wasn't to revert to single-speed austerity, but to find a middle ground, a system that offered practical gearing for urban and light trail riding without the intimidating intricacy of 20-plus gears. The result was the 5-gear direct drive, a system that radically rethought the power transfer from pedals to wheel. Instead of a single large chainring at the front and multiple smaller cogs at the back, Tim's design featured a series of 5 interconnected gears, all positioned centrally along the bicycle's frame. This direct drive approach eliminated the need for a rear derailleur entirely, as the gear changes happened within this enclosed, central system. The core of the innovation lay in how these 5 gears interacted. A primary chainring, connected to the pedals, would drive a series of intermediate gears. These intermediate gears, cleverly designed with varying tooth counts, would then, in turn, drive a final gear connected to the rear wheel. Shifting would occur not by moving the chain between cogs, but by engaging and disengaging specific intermediate gears within the central housing, potentially through a simple, robust internal mechanism controlled by a single shifter. This meant the chain always ran in a straight line, reducing wear and improving efficiency. The advantages were immediately apparent. With fewer moving parts exposed to the elements, maintenance would be drastically reduced. The system would be inherently more durable, less prone to damage from impacts or debris. Shifting would be crisp, immediate, and intuitive, free from the clunky adjustments often associated with traditional derailleurs. For the average rider, who primarily navigated moderate terrains and sought reliable, fuss-free operation, this simplicity was a revelation. However, the unconventional placement of the gears presented a new challenge: rider safety. With the intermediate gears positioned centrally and potentially exposed, there was a risk of clothing, shoelaces, or other fabric getting snagged in the rotating teeth. Tim recognized this immediately. His solution was an essential, integrated safety feature, a robust guard that would completely encase the top and sides of the exposed gears. This guard wouldn't be an afterthought, it was an integral part of the design. Crafted from a strong, lightweight composite material, it would sit snugly over the entire gear cluster, forming a protective barrier. Its smooth, aerodynamic profile would not only prevent fabric entanglement but also shield the gears from dirt, dust, and splashes, further enhancing the system's longevity. Invention 8, Electrolock, the invisible guardian. For as long as bicycles have been a primary mode of transport, the battle between owner and thief has been a wearying arms race. We have seen heavy steel chains, cumbersome U-locks, and folding plates, all designed to make a thief's life difficult. Yet, these traditional methods share a common flaw: they are external, often bulky to carry, and vulnerable to the relentless bite of a bolt cutter or the high-pitched whine of an angle grinder. The security was always an add-on, something separate from the machine itself. Tim, observing the sleek lines of his modern frame designs, felt that security shouldn't be an aesthetic burden or a logistical chore. He envisioned a bicycle that protected itself from within, a sentinel integrated so seamlessly into the architecture of the bike that a thief wouldn't even realize the trap was set until they tried to make their getaway. The mechanism of motionless security. The Electrolock is the culmination of this vision. Unlike a traditional lock that tethered the bike to a stationary object, the Electrolock was designed to immobilize the machine's most vital component, the rear wheel. The heart of the innovation is a high-tensile, horseshoe-shaped bolt integrated directly into the seat stays, positioned just above the rear tire. When disengaged, the bolt sits flush against the frame, invisible to the untrained eye and offering zero resistance to the spinning wheel. However, once activated, the electronic actuator drives the reinforced bolt downward through the spokes, effectively turning the bicycle into a stationary sculpture. By locking the wheel directly to the frame, the Electrolock eliminates the easy getaway. Even if a thief manages to bypass a secondary cable or simply finds the bike leaned against a wall, they cannot ride it away. A bicycle that cannot roll is a liability to a thief. It requires being carried, a conspicuous and difficult act that drastically increases the chances of being caught. Fabric safety and the integrated guard. Innovation, however, is never without its practical hurdles. During the prototyping phase, Tim identified a critical safety concern regarding the proximity of the locking rotors and the moving wheel to the rider's clothing. In a system where mechanical parts sit so close to the seat post, there was a risk of loose fabric, a long coat, a flowing skirt, or even wide trousers getting caught in the mechanism or the spokes. To solve this, the 352 Electrolock features an essential integrated rotor guard. This sleek, low-profile shield sits atop the locking mechanism, acting as a physical barrier between the rider's clothing and the moving parts of the wheel unlock. This guard ensures that while the bike remains a fortress against theft, it remains perfectly safe for the rider, preventing any accidental snagging during high-speed commutes or casual rides. The electronic interface. The true magic of the 352 lies in its activation. Abandoning the physical key, a small object easily lost or picked, Tim integrated the system with modern smartphone technology. Through a dedicated, encrypted app, the rider can engage or disengage the lock with a simple tap on their screen. The system can even be set to Auto Sentinel mode, using proximity sensors to detect when the owner's phone moves more than 10 meters away, automatically sliding the bolt into place. Invention 9, the easy launch. The city was a symphony of motion, a blur of commuters, taxis, and the ubiquitous whir of bicycle wheels. Amidst this organized chaos, avid cyclist Tim often found himself in a familiar dance at every red light: dismount, steady the bike, wait, then the awkward remount. It was a minor inconvenience, yet it broke the rhythm of his ride, especially during peak hour. He yearned for a seamless transition, a continuous flow that wouldn't interrupt his cycling journey. Tim was a thinker by nature, his house a testament to his inventive spirit. Spare parts, circuit boards, and half-finished prototypes adorned every surface. His current obsession, the auto stand, a concept that had been brewing in his mind for months. He envisioned an electric kickstand that would deploy automatically as his bike came to a stop, eliminating the need to ever put a foot down. His latest prototype lay splayed across his workbench, a crude but promising sketch serving as his blueprint. The core of his idea was a sensor-activated mechanism, subtly integrated into the bicycle's frame. As the bike's speed dropped below a certain threshold, the sensor would trigger a small electric motor. This motor, powered by a compact, rechargeable battery, would then gracefully extend the kickstand. Tim imagined the stand extending in a smooth, almost imperceptible motion, holding the bike upright as he paused, feet still clipped into his pedals. When the light turned green, a slight push on the pedals would signal the stand to retract, a swift, silent motion that would launch him back into the flow of traffic without a hitch. He had also designed a manual override, a small button conveniently placed on the handlebars for those moments when a quick, controlled stop was needed, independent of the sensor. This also allowed for a faster launch option, where the stand would retract almost instantaneously, giving the rider an extra edge in the urban race. The challenge wasn't just in the mechanics, it was in the seamless integration. The auto stand needed to be lightweight, robust, and aesthetically pleasing. It couldn't disrupt the balance or the sleek lines of a modern bicycle. Tim spent countless nights hunched over his workbench, soldering wires, testing microcontrollers, and sketching intricate diagrams. His initial attempts were clunky, the motor whirring loudly, the stand deploying with an ungraceful lurch. But each failure was a lesson, each setback a step closer to his vision. His most recent iteration involved a dual motor system, one for deployment and one for retraction, allowing for greater control and a smoother action. He'd sourced miniature, high-torque motors, usually found in drone technology, for their efficiency and compact size. The battery pack, he decided, would be integrated into the seat post, discreetly hidden from view. As the morning sun streamed through his window, illuminating the intricate workings of his design, Tim felt a surge of anticipation. Today was the day. He had refined the sensor sensitivity, optimized the motor's torque, and meticulously balanced the weight distribution. He carefully packed his tools, his helmet, and the almost complete auto stand prototype into his backpack. The bustling Melbourne city awaited, and Tim was ready to test his creation, not just as an invention, but as a promise of a smoother, more elegant cycling experience. The dream of the perfect stop and launch was within reach. Invention 10 Lever of torque. Tim's mind wasn't only on the auto stand, another innovation buzzed in the periphery of his thoughts, a concept born from countless hours spent analyzing cycling mechanics. He called it the extended pedal system. The basic premise was elegantly simple, a bicycle pedal that could manually extend or retract, altering the effective crank length and, consequently, the leverage applied to the drivetrain. He had sketched out the core idea on a fresh page of his notebook, the diagram showing a pedal arm with clear segments indicating points of extension. Extend for speed and torque, he'd scrawled beside an arrow pointing outwards from the pedal. The opposite action, though not explicitly labeled, was just as critical, retracting for higher cadences and different riding conditions. The existing fixed-length pedal cranks, Tim knew, were a compromise. A longer crank offered greater torque, ideal for climbing steep hills or accelerating from a dead stop. A shorter crank allowed for a higher cadence, crucial for maintaining speed on flats or during sprints, reducing the strain on leg muscles over long distances. But what if a rider didn't have to choose? What if they could dynamically adapt their leverage on the fly? Tim's design incorporated a robust, yet lightweight, telescoping mechanism within the pedal arm itself. A small, almost imperceptible button or lever, placed within easy reach on the pedal's surface, would activate an internal spring-loaded system. Pressing it once would extend the pedal, lengthening the crank arm by a predetermined increment. Pressing it again would retract it, returning it to its original, shorter configuration. He envisioned a series of detents, allowing for perhaps 2 or 3 different lengths, each optimized for specific situations. For instance, a cyclist facing a punishing uphill climb could extend their pedals, gaining the extra leverage needed to grind their way to the summit with less effort. Conversely, on a long, flat stretch, or when navigating a technical descent requiring rapid leg movements, they could retract the pedals, achieving a higher, smoother cadence. The immediate challenge, Tim knew, was reliability and durability. The mechanism had to withstand immense, repetitive forces. Any play or wobble in the extended pedal would not only be inefficient but potentially dangerous. He had begun researching materials like high-grade aerospace aluminium and carbon fiber composites, looking for the perfect balance of strength, stiffness, and minimal weight. The spring mechanism, too, needed to be flawlessly engineered, strong enough to engage and disengage crisply, yet smooth enough not to jar the rider. He also considered the rider interface. The activation mechanism needed to be intuitive, allowing for changes without breaking concentration or requiring awkward maneuvers. A small, tactile button that could be pressed with the side of a cycling shoe seemed the most promising. As he stared at his sketch, the lines, though simple, represented a profound shift in cycling dynamics. It wasn't just about speed or torque, it was about efficiency, comfort, and adaptability. The extended pedal system, coupled with his auto stand, could transform the cycling experience, making it more fluid, more powerful, and utterly responsive to the demands of the road. The city outside beckoned, a diverse tapestry of inclines, flats, and bustling intersections. Invention 11, the unseen guardian, automated chain care for the modern cyclist. The rhythmic whir of a well-maintained bicycle chain is music to any cyclist's ears. It speaks of efficiency, longevity, and a smooth transfer of power from pedal to pavement. Yet, this vital component, exposed to the relentless assault of grit, grime, and the elements, often suffers from neglect. Traditional chain maintenance, a messy and time-consuming affair, remains a significant barrier for many riders, leading to premature wear, reduced performance, and the dreaded squeal of a protesting drivetrain. But what if the chore of chain cleaning could be relegated to the past, replaced by an elegant, on-demand solution? Imagine a device so seamlessly integrated into your bicycle that its presence is felt only in the effortless glide of your chain and the extended life of your components. This is the vision behind the automated chain cleaner, a silent guardian poised to revolutionize bicycle maintenance. At its core, this innovation reimagines the very act of chain cleaning. Gone are the days of wrestling with brushes, degreasers, and rags. Instead, a compact, unobtrusive unit is strategically positioned along the chain's path. This unit, far from a mere static brush, houses a sophisticated array of metal bristles, precisely engineered to dislodge and sweep away accumulated dirt, rust, and debris without damaging the chain's delicate linkages. The true stroke of genius, however, lies in its activation. Envision a slender, robust cable, subtly routed alongside your brake and gear lines, connecting the cleaning unit to a discrete lever or button positioned conveniently on your handlebars, or perhaps even a more integrated control point on the frame. This ergonomic placement transforms chain maintenance from a scheduled task into an instantaneous, responsive action. Imagine this scenario: you're halfway through a muddy trail ride, the fine grit of the path beginning to gum up your chain. Instead of enduring a noisy, inefficient return journey, a simple flick of a switch or press of a button engages the cleaning mechanism. The metal bristles spring to life, gently but firmly scouring the chain as it passes through the unit. The immediate benefits are manifold. On-demand cleaning, no more waiting until the chain is heavily fouled. A quick activation during or after a ride prevents stubborn buildup. Extended component life, by consistently removing abrasive particles, wear on the chain, cogs, and chainrings is drastically reduced, saving riders significant costs over time. Enhanced performance. A clean chain is an efficient chain. Reduced friction translates to smoother pedaling, quieter operation, and a more enjoyable riding experience. Convenience and cleanliness. The messy aspects of chain maintenance are contained, keeping hands and clothing free from grease and grime. Versatility. The design allows for adaptability across various bicycle types, from urban commuters battling city grit to mountain bikers conquering muddy trails. The engineering challenge was considerable: how to create a unit that is robust enough to withstand the rigors of cycling, yet precise enough to effectively clean without hindering chain movement. Invention 12. The friction anchor, reimagining the Plan B braking system. In the rugged highlands of North Albania, innovation wasn't born in a laboratory, it was born on the steep, rocky descents of mountain passes. For the children of Kabash, a bicycle was often a patchwork of salvaged steel and determination. When the simple rim brakes failed, or simply didn't exist, survival depended on a singular, instinctive maneuver, the drag. It was a childhood rite of passage to sacrifice the soles of one's shoes to the gravel to avoid a collision. Decades later, this visceral survival tactic has inspired a sophisticated leap in cycling safety: the friction anchor support system. The anatomy of the reinforced toe. Traditional cycling shoes are designed for one thing: power transfer. They are stiff, lightweight, and fragile. The friction anchor turns this philosophy on its head. The shoe features a dual-density dorsal shield, a rugged, heat-resistant support structure positioned directly above the phalanges, the foot fingers. Unlike a standard toe cap, this reinforcement isn't just for protection against rock strikes. It is an integrated friction pad made of a silicon carbide composite, similar to the materials used in high-performance automotive brake pads. This shield is ergonomically molded to allow the rider to transition from a pedaling position to a planned position in milliseconds. The emergency protocol. In the world of high-speed cycling, a Plan B is rarely available. If a hydraulic line snaps or a rim becomes slick with oil and rain, the rider is at the mercy of momentum. The friction anchor provides a secondary deceleration circuit. When an emergency is detected, the rider unclips and executes a controlled, forward toe plant. The extra support above the foot fingers provides two critical functions. Structural integrity. It prevents the foot from collapsing or sustaining turf toe injuries under the immense pressure of the road's drag. Thermal dissipation. The composite material is engineered to handle the flash heat of friction, protecting the rider's foot from the scorching temperatures generated by the pavement. From childhood instinct to modern engineering, the beauty of this innovation lies in its cultural DNA. What was once a desperate move by a child on a dusty Balkan road has been refined into a calibrated safety feature. The shoe doesn't just stop the bike, it provides a sense of grounded control. By lowering the center of gravity and creating a third point of contact with the earth, the rider can stabilize a wobbling frame while shedding velocity. This system serves as a bridge between the raw, intuitive cycling of our past and the high-tech, safety-conscious future of the sport. It acknowledges that sometimes, despite all our gears and gadgets, the most reliable way to stop is to return to our roots, putting our feet firmly on the ground. Invention 13. The Bigfoot pedal. Embrace the breeze, embrace the ride. The joy of summer cycling often clashes with the rigid demands of traditional pedal systems. Clipless pedals, while efficient, tether you to your bike, requiring specialized shoes and a practiced dismount. Flat pedals, though versatile, can still feel restrictive, especially when the mercury rises, or you simply want the freedom of a spontaneous stop to dip your toes in a stream. For those moments, for those sun-drenched days of effortless cruising, we introduce the Bigfoot pedal. Inspired by the ultimate freedom of walking barefoot, the Bigfoot pedal is a revelation for casual cyclists. It's an open, expansive platform designed to liberate your feet, allowing you to ride comfortably in anything from sandals to bare feet, or even your favorite pair of sneakers, without sacrificing control or comfort. This isn't just a pedal, it's an invitation to experience cycling in its purest, most uninhibited form. Designed for comfort, defined by freedom. At first glance, the Bigfoot pedal's most striking feature is its generous, ergonomic surface. Unlike the narrow confines of standard pedals, this design provides ample room for the entire foot, mimicking the natural stance of walking. The broad metal plate at its core isn't just a robust foundation, it's engineered for optimal pressure distribution, reducing hot spots and fatigue on longer, leisurely rides. This means you can cruise for hours, feeling connected to your bike without the discomfort often associated with smaller pedal surfaces. But the true genius of the Bigfoot pedal lies in its adaptability, effortlessly shifting between two distinct modes to match your riding mood. Cruise mode. This is the default, relaxed setting. The pedal's broad, open framework embraces your foot, providing a stable, reassuring platform. The grip elements are gentle yet effective, ensuring your foot stays put without being abrasive. This mode is perfect for leisurely rides along the beach, through quaint town streets, or on a relaxed commute where comfort and the ability to easily put a foot down are paramount. It's about soaking in the scenery, not chasing KOMs. Race mode. Even casual riders sometimes crave a burst of speed or need a bit more control. With a simple, intuitive adjustment, perhaps a flip mechanism or a quick-release lever, the pedal subtly reconfigures, offering slightly more aggressive grip points and a more defined foot placement. While still retaining its open design, race mode provides the enhanced connection needed for a short sprint to catch a green light or navigate a slightly more challenging incline. It's a nod to versatility, giving you options without demanding special footwear. The barefoot advantage. The ability to cycle barefoot or in open-toed shoes isn't just a matter of comfort, it's about connecting with the environment. Imagine pedaling along a coastal path, feeling the warm breeze on your skin and the sun on your feet. With the Bigfoot pedal, there's no need to carry extra shoes or worry about sweaty, confined feet. It's about the pure, unadulterated sensation of movement, of effortless glide. This pedal isn't for the competitive racer or the aggressive trail rider. It's for the free spirit, the urban explorer, the weekend wanderer who values simplicity, comfort, and the sheer joy of the ride. Chapter 14, A Sanctuary for a Modern Machine. For the dedicated cyclist, a bicycle is far more than a collection of tubes and gears. It is an extension of the self, a partner in exploration, and a high-performance machine that deserves meticulous care. Yet, the ritual of the bicycle wash has long been a cumbersome affair, often relegated to cramped apartment bathrooms or the imprecise blast of a garden hose. This chapter explores the emergence of the dedicated bicycle wash station, a purpose-built sanctuary designed specifically for the unique geometry and delicate components of the modern bicycle. The architecture of cleanliness. The concept of a professional bicycle wash begins with a fundamental shift in design philosophy. Unlike a standard car wash, which relies on high-pressure volume that can force water into sensitive bearings, the bicycle wash is a study in precision and ergonomics. As illustrated in the conceptual bicycle wash schematic, the station is organized around an intuitive user interface. Integrated control panel. A select dial allows the rider to choose specific programs tailored to their needs, ranging from a gentle dust rinse to a deep drivetrain degrease. Specialized spray wands. The wash features ergonomic, low-pressure wands designed to reach into the intricate spaces between spokes, chainrings, and brake calipers without risk of damage. The drainage matrix. Strategic floor grates are positioned to instantly channel away runoff, keeping the user's feet dry while capturing oils and contaminants before they enter the water system. A ritual of preservation. The true value of a dedicated wash station lies in its ability to facilitate preventative maintenance. When a bicycle is cleaned in a space designed for it, the rider is better able to inspect the frame for hairline fractures, check tire wear, and ensure that the drivetrain is free of abrasive grit. This station is more than a convenience, it is a hub for the cycling community. It represents a respect for the craft of cycling and an understanding that a clean machine is a fast, safe, and enduring machine. By providing the right tools and the right environment, the bicycle wash transforms a chore into a ritual of preservation. Invention 15. The flotation variable, engineering the gear wheel for soft terrains. In traditional cycling, the goal is often to minimize the contact patch to reduce rolling resistance. However, when the substrate changes from asphalt to loosely packed sand or wind crust snow, the objective flips. We must maximize the surface area to prevent shear failure of the ground. 1. The physics of flotation. To float over sand, the wheel must satisfy the pressure equation. P equals AF, where P is the ground pressure, F is the downward force rider plus bike weight, and A is the contact area. By utilizing the flat gear shape seen in the design, the wheel creates a wider, more stable rectangular footprint compared to the elliptical footprint of a standard tire. 2. The flat gear shape advantage. The design features deep, blocky lugs arranged in a gear-like fashion. This serves two primary purposes. Paddled propulsion. In deep sand, the tire acts less like a rolling circle and more like a paddle wheel. The vertical faces of the gears bite into the sand, using the material's own internal friction to provide forward thrust without digging a hole. Structural flotation. The flat profile ensures that weight is distributed evenly across the width of the rim. This prevents the knife effect, where a narrow tire slices through the surface crust and sinks to the rim. 3. Adaptation for hardened snow. While sand is fluid and granular, hardened snow crust behaves like a brittle solid. To adapt the sand wheel for snow, two modifications are necessary. Invention 17. The support skeleton, ergonomics for the ultra-endurance tourer. In traditional long-distance touring, the primary enemy is not the terrain, but cumulative fatigue. When a rider spends 8 to 12 hours in the saddle, the stabilizer muscles in the core and hips begin to fail, leading to poor form, joint misalignment, and eventual injury. The extended fulcrum frame F introduced in this design is engineered to act as a leaning skeleton, shifting the burden of support from the rider's soft tissue to the bike's rigid geometry. 1. The active lean concept. Unlike a standard diamond frame bike where the rider must actively hold their body in a specific posture, the F design allows for passive stabilization.